Hey Matt, 30-1. Okay, so we're getting into new unit, permutations, combinations, and binomials. It's going to be a pretty fast one. So what this one is about is really the number of ways things can happen. That's what we're going to be doing first. And then binomials are kind of like their own little twist, but permutations and combinations are pretty much figuring like, the number of ways that you could choose two students from a group of 50 or something like that, right? Yeah. So first off, to get our bearings here, we use something called the fundamental counting principle. And all this really is, right, is if let's say that you know, four you had four different colors of shirts and you had or four different shirts and you had three different pairs of pants. So how many different outfits could you actually make? Well, the fundamental counting principle just says that you just multiply the number of ways. So if you had four shirts, that would just be four times my three pants. So there's 12 different outfits you could wear, right? So that's pretty much it. We just multiply the numbers when we're kind of figuring out how many ways that could happen. Yeah, so let's jump into this example. It's kind of the same thing, but just another twist on it. So it says many video games over the years have incorporated some version of a three-part key sequence to unlock some portion of the game. For example, if there are three chains that have to be pulled in a certain order to unlock the door, how many different combinations are there? Okay, actually, technically, that would be how many different permutations are there, but we quite often say combinations. We'll get into what combinations really are in the next or the lessons from now. But all right, so here's the idea. So you got like, let's say, chain number one, chain number two, and chain number 1, 2, and 3. And we have to pull those in a certain order to unlock the door, right? Okay, so fundamental counting principle, we just do it this way. We say, okay, how many ways are there for my first pull? Well, I could either pull 1, 2, or 3. So we'd say there's 3 different ways that could happen. So I like making these blanks. You'll see me doing that quite often, where this is like my first option. And then after that, the way this works is after I pulled that first chain, how many chains do I have left to pull? Well, I only have 2 left. And then after I pulled the first chain and the third chain, how many options do I have left? Well, I only have one option left. And then the fundamental counting principle says we just multiply the number of ways. So there would be 6 different ways that we could pull the chain, right? Okay, so 6 ways. Now it says prove your result with a tree diagram. So a tree diagram kind of just spells it out. So an example of that, let's say if I did pull, let's say chain number 1, right? Then after that, I have 2 options. I could pull chain number 2, or I could pull chain number 3. And let's say if we pulled chain number 1 and then we pulled chain number 2, well then after that I have to pull chain number 3, right? So that's like one path, right? Through is that one, where that could have been the situation that happened. Or if I pulled chain number 1 and then chain number 3, well the next one would be to pull chain number 2. And there's another path. And then we're just really going to write out all the different paths that we have here. So then the next one would be, well, we could have pulled chain number 2. And then if I did that, I could pull 1 or 3. And then if I pulled 1, I would have to pull 3. If I pulled 3, then I'd have to pull 1. Right? So there's 2 more paths. There's 2 more situations that could have been the case. And then the last one was if I pulled 3, then I would have to pull either 1 or 2. And then this would be 2 and 1. And there you go. And you can see that I literally have 6 different situations that could have happened. So there'd be 6 ways. Okay. And that's called a tree diagram because it looks like a tree. Yeah. All right. Next one here. So it says license plates in a certain country consist of 6 characters. The first 4 can be any continent, and the last 2 have to be different numbers. How many license plates can be made under this system? Okay, so again, what I like to do is make my blanks. So we got 1, 2, 3, 4, 5, 6 blanks. Now it just kind of tells us which things are allowed in the first, in our certain blanks here. Okay, so now, yeah, we'll just kind of do what they ask here. So it says the first 4 can be any constant, all right? So this just requires that we know how many, I guess, constants are in the alphabet. Yeah, there are 21. You could count them out. But anyway, so there's going to be 21 could be in the first spot. And then 21 in the second, right? There's 21 in that option. And then 21 and 21, right? So that many options for my first one. And then we move down to the last 2. So it says the last 2 have to be numbers. So how many, so this one always trips people up too. So how many different numbers are there? Well, if we've got the numbers 0 to 9, well, that's actually 10 numbers, right? From 0 to 9 because you count 0. So there'd be 10 for that one and 10 for that one. And then, yeah, we're kind of set up there, right? So we multiply when we write them all out like that. So in the end, we get, what do we get? Large number. 17,503,290. All right, next one. So it says the paper on which you wrote your new friend's phone number was torn and the last 2 digits were lost. You remember that the digits were not the same. How many 10-digit phone numbers might you have to try to guarantee you find the right one? All right, so 10-digit phone numbers. So you could write our digits here, right? So we have 1, 2, 3, 4, 5. Actually, you know what? I'm going to put them in groups of 3, like phone number. All right, so if we're trying to figure out the number of digits, well, technically they told us it was just the last 2 that we didn't really know, right? So in this case, the first number we did know, right? So we can actually say, well, there's 1. It has to be like whatever number it is, right? So there's one way that can happen. 1, 1, 1, 1, 1, 1, 1, right? We know all these. We know that those ones, we know that those ones, and we know those ones. So really 1 times 1 times, yada, yada, yada. That's all just 1, right? The only thing that was really of interest here was these last 2. So right off the bat, I could have just ignored that and said, well, how many ways do I have to rearrange these last 2 numbers, right? So that's not too bad. So then if we're doing that, then all we have to do is say, well, okay, well, for this first number, well, there's 10 possibilities for that. And then it says, though, that they were different numbers, right? So how many possibilities are there for the second one? Well, now there's only 9 because we chose 10 for the first one, right? So then in the end, there's 90 possibilities. All right, next one. In how many ways can a teacher seat 4 girls and 3 boys in a row of 7 seats if a boy must be seated at each end of a row? Okay, let's get our bearings here. Let's write out our lines again. So we'll do 7 seats, right? So we got 1, 2, 3, 4, 5, 6, 7. And now they told us that in the first spot and the last spot, right, at the end of each row, there must be a boy, right? Well, how many boys do we have to choose from? There's 3 boys. Okay, well, let's say we just look at that first spot for a second. How many ways are there to put a boy there? Well, there's 3 to choose from, right? And then I'll do the end now too, like while we're at it. If I've chosen one of the boys, now how many are there to choose for the last one? Well, now there's 2. And now that I've done that, right, now I can just say, okay, well, the rest of the people, right, everything else in the middle here, it doesn't really matter, right? I don't care who's a boy and who's a girl. There's 5 people left, right? There was 4 girls and 1 boy left, but either way, there's 5 possibilities for that one, and then 4, and then 3, and then 2, and then 1. Okay, and that's it. So once you get all those, then you know the deal. You just multiply them all together. So we end up with 720. So 720 different possibilities. Okay, now next one, it says there's no restrictions. So for this one, all we're going to do, we'll just write out our blanks again. Okay, And then, okay, no restrictions. Then that just means I don't care who's boys, I don't care who's girls. We have 7 people, right? So in the end here, it's just, well, there's 7 for the first spot, and then there'd be 6 for the next, and then 5, 4, 3, 2, and 1. Okay, and that's it. So that one's even easier, right? So that one's 5,040 possibilities for that one. Alrighty. Now, complete the following. Cam is determining how many odd 5-digit numbers there are. And this one can be a little bit deceiving, right? Because it might not tell you this last part. It's up to you to know this. Is that how many odd or how many 5-digit numbers there are in the first place, right? Is that the first number is not allowed to start with 0, right? Because like this situation, you wouldn't call that a 5-digit number, right? That'd be a 4-digit number. So the very first spot, like when we make our blanks here, we're gonna have 5 spaces here, but the very front spot, we have a restriction on this, right? How many ways can the first one go in? Well, typically there'd be 10, right? Because you'd have 0 to 9, but this one can't be 0, so there's only 9 ways that can happen, right? So you can write this and be like, you can say that it can't equal 0 to remind yourself or what I'm doing there. Okay. And then the next spot, well, the next spot you could have any number. So 10, and then 10, and then 10. But then just be careful in the last one, right? So just remember we're talking about odd 5-digit numbers. So odd numbers would end in, well, an odd number, right? So the possibilities for here have to be 1, 3, 5, 7, or 9, right? So it could be one of those, but that's it. Okay, so then this has to be 5. So that's to end in one of those. Okay, so now we can just multiply all together. And we get 45,000. So these can be tricky, so just take your time on these. Okay, so yeah, speaking of little tricky questions here, this one could be a little tricky in particular. So let's read it first. Now Cam is determining how many even 5-digit numbers there are, and this time there's no repeating digits allowed, right? Last time we were allowed to just repeat, like, there was 10 for that one, 10 for that one, right? But this one's going to change. So let's write down our blanks to kind of see what we're dealing with here. So 2, 3, 4, 5. All right. So now, just like the last one, we're going to say, okay, can't be 0 for the first one, right? Let's look at the last part here, right? So if it's an even number, then this thing would end in 0, 2, 4, 6, or 8, right? So you might be tempted just to say, okay, well, same as last time. Let's just make this 9, right? Because it can't be 0, and you go maybe like 9, 8, 7, yada yada, and then the last one would be 5. But the only issue is here, right? Is that since we're dealing with the not repeating part of it, whatever I choose, right? Whatever I choose for this, right? Let's say that I chose a 2 to go in there. Well, what happens now is that the number out front can't be a 2. If I chose a 4 for the last one, then the number out front can't be a 4. You kind of see what's happening here is that instead of this being 9 like it was last time, it's actually only going to be 8 because it can't be the number that we have on the end. But that being said, let's take a closer look at this 0 too, right? Let's for a second just assume that I put a 0 in there. Well, if I put a 0 in there, now how many possibilities are there for that one? Well, there's actually 9, right? Because remember, it never could be 0, right? It was never allowed to be 0, so there was 9 in that case, right? So we run into an issue here where we have to split this thing up. We have to come up with different number of ways. So what I'm going to do is I'm going to set up one situation where the last number is not 0. Here, so let's write that out. Last number is not 0. Okay, so that's this scenario. So let's do that first before we keep going. So this one, if it's not 0, then I only have 4 options there. So in this case, the first one here would be, well, 8, like we said, right? Because it can't be 0, and then it can't be the number in the end. So there'd be 8 possibilities for the first number. Okay. Now that we've chosen that number, you might think that we're just going to say, okay, there's 7 possibilities now. But that's actually not quite right, because this one now can be 0, right? This one's allowed to be 0, so that like adds one more, right? So there's actually 8 possibilities now for that second spot. And then after I've chosen both of those two, now there's only 7, and then there's only 6, right? So that's kind of like that pattern that we saw above, right? Like in this example with the restrictions of 7, 6, 5, 4, like you just count down like that. But that front part can be a little confusing. And then the last number here, well, there's just 4 possibilities, right? There's 2, 4, 6, or 8. Okay. So if we add that all, or multiply all that together, then there is 10,752 possibilities, right? But then don't forget, we also have the other situation, right? The other situation was when the last number is 0. Okay, so we have to do it all again now. So we'll make our blanks. So again, we can say, well, the front number there is not allowed to equal 0. Never is. Okay. And then how many options do we have for the last spot? Well, it has to be 0, right? That was the whole point. The last number is 0. So there is, well, one option for that, right? It's equal to 0. Hopefully that makes sense. Okay. So then, okay, well, then there's only 9 possibilities. And I don't have to worry about, this one already being chose because it's 0, right? The front number was never allowed to equal 0. Okay, so there's 9 possibilities, everything but 0. And then after that, well, then there's 8, and then 7, and then 6 possibilities. So if we multiply those together, we end up getting 3,024. Okay, so now, in this situation, we split it up, right? There was this many ways, and then also this many ways, okay? So in this situation, we're not going to multiply them. We add these together. These are like different cases. This is like case number 1, and this is like case number 2. So we just add those different situations up. So we'd say, okay, there is 10,752 plus 3,024. So we end up with 13,776. All right, like I said, I'm gonna be a little tricky, and then this one's gonna seem really simple now in hindsight. Okay, so now this one says how many odd or even 5-digit numbers are there, and repeating is allowed. Okay, well, yeah, this one's pretty straightforward because now we just have to remember that the front number cannot equal 0, so there's only 9 ways for that to happen. But then after that, if repeats are allowed, then this number could be anything, right? This could be all the numbers from 0 to 9. So there's 10 of those, 10 of those for the next one, 10 of those, 10 of those. Okay, so there is 90,000 different ways. Okay, moving on. How many different 4-letter arrangements can you rearrange from the word question? Okay, so now any letter can be in any position. All right, so again, how many different 4-letter words? So I'm going to draw 4 blanks. And then I'm going to look at the very first letter. How many options are there, right? There's no restrictions, says any letter can be in any position. So really, I'm just wondering how many different letters there are, right? There's 1, 2, 3, 4, 5, 6, 7, 8 to choose from. Okay, so in that first spot, I could have 8 to choose from. There's 8 different ones. Okay, and now this is the situation though, like where order does matter, right? Where there's not going to be 8 for the second one because I can only choose from these letters, right? I can't have 2 Q's in a row or 2 S's in a row, right? Because I have to choose the different letters. So now there's only 7 after I've chosen the first one, and then 6, and then 5. Okay, so that, if you multiply those together, we end up getting 1,680. All right, the first and the last letters must be consonants. All right, so again, let's make our 4 letters. Now it says the first and the last one must be consonants. Well, I got to figure out how many of those I have. So I only have, well, Q, S, T, and N, right? Those are my only consonants. Okay, so there's 4 to choose from. So let's look at that first spot. I could put any of those 4 in the first spot. And it says the last letter must also be 1. So if I go to the last letter and say, okay, well, I've already chosen 1. So I've only got 3 now to choose from. And then after that, I'm kind of good to go, right? I've got the rest of them. But just remember, we've already chosen 2 of these consonants. So how many do I have left, right? So there's 6. There's 6 different to choose from after I've chosen those. So there's 6. And then after I've chosen that one, then there's only 5 possibilities for the next one. All right. The first letter must be a T. So let's do the same thing with the 4 blanks. So my first letter must be a T. Well, how many ways are there for the first letter to be a T? Well, 1. It has to be a T. Okay. So then after that, I just know I've already used the T. So then I can just use the rest of the letters, right? So there's only 7 left now. So now I'm just going to go 7. And then the next one would be 6. And then 5. All right. Now, again, this one can be a little bit tricky too, right? It says the word must contain N. Like it has to have N in it. So let's do our blanks again. So we'd have 1, 2, 3, 4. Now, here's the issue, is that I could say, okay, well, let's put an N in the first spot, right? And how many ways can that happen? Well, there's 1. And then you'd have 7, 6, and 5, kind of similar to the first one, right? But what if the N was in the second spot? So again, this is where we're going to have like our cases, right? Where this will be like case number 1. And then I'm going to add it to case number 2, where we can have N in the second spot. So we'll have our blanks again. But this time N's going to go here. So there's 1 way for that to happen. And then you'd have 7, 6, 5. And then in the second spot, you'd have, well, the same thing, right? You're probably seeing where I'm going here. But our blanks, N has to be in the third spot. So then there'd be 7, 6, 5. There was 1 way for that to happen. And then it could be at the end. So, N's at the end, 1 way, and then 7, 6, and 5. Okay, so if you do all that, you would have got, well, this would have been 210. This would have been 210, and yeah, all 210, right? Okay, so you end up getting 840. Well, you probably saw a pattern there too, right? This is fine. You could write it all out with the different cases, right? Like this is 1 case, 2 cases, 3 cases, 4 cases. But the other thing you could have done, right, if it asked to simplify it or something like that, is you could have said that this was the same thing as 210 times 4, right? Maybe I won't write it there. This would all be the same thing as 210 times 4, or like 7 times 6 times 5 times 4, right? That would actually get you the same number just because there's 4 of them, right? They're all the same. All right. All right, so one thing to note here is that anytime you have to distinguish components of a question with the word and, that represents a multiplication between the digits. So something and something else, right? That'd be like our fundamental counting principle. If you were going to wear, if you had 4 different shirts to choose from and 3 different pairs of pants, you would multiply those to figure out the number of outfits, right? But if it was, if you see the word or, then that's going to be addition, right? If it's this thing or that thing, right? So it's like the n could have been in this spot or this spot or this spot or this spot. Then we add those situations together. Okay. And then anytime there is a restriction, did you guys notice that? Yeah, that's what I was kind of doing, like in this example, right? Where I said, okay, I put the consonants there and there first, and then filled in what was left. So I did the restrictions first. All right, next part. So factorial notation. So whenever the numbers descend from the largest number all the way down to 1, we actually have a notation for this in math. It's called factorial notation. Okay, so we had a couple of examples above where we had this situation where it was like 6 times 5 times 4 times 3 times 2 times 1. In math, we write that as 6 factorial with like an exclamation point. Okay, it's different places on your calculator. You'll find it under, one sec. So on a TI-84, you're going to find it under math and then probability. And actually same thing on the TI Inspire, but on the TI Inspire, you'll also find it down in the bottom right. You'll see you have like a bunch of like symbols like, question mark, factorial and stuff. So you should find that there, and then you can write it in. If you type in 6 factorial, it would actually do the same thing as writing out 6 times 5 times 4 times 3 times 2 times 1. Okay? So now, in general, this is how we can write out factorial notation with any number, right? So this is just like a variable n. So this actually is saying the same thing as above, but just like I said, like in a general expression. So in this case, right, if n factorial, there was like 5 factorial above, well, that would be, okay, so that would be n, or 5. Okay, so yeah, n would be like our 5, right? That's where we're starting. And then the next one was 4. And do you see how 4 is just 5 minus 1? Well, that's where this comes from, right? N minus 1. And then 3 is really the same thing as 5 minus 2. So that's that one. And then we just keep on going down. And then the way this is written, it goes dot, dot, dot. It just means that there's going to be some stuff in the middle. But either way, we're going to end at 1, right? So either way, we're going to end at going like down to like, down to 3, 2, and then to 1. Okay? Yeah, so let's do some examples here. So we can actually do some math with factorials too, right? If we kind of write these things out. So like in this case, if we had 7 factorial over 3 factorial, that would be the same thing as 7 times 6 times 5 times 4 times 2 times 1, right? That's what 7 factorial is. And then if I divide that by 3 factorial, that's really 3 times 2 times 1. You see how that's the same thing as just canceling out all those? So this would all be equal to 7 times 6 times 5 times 4. Okay, so in the end, yeah, you could also just actually write the answer out. So those would be the same thing as 840, doing it that way. But actually, one thing here too, I just want to kind of show you, I could have written this a little different. I should have done that from the beginning. This would have been the same thing as 7 times 6 times 5 times 4 times, and I could have stopped it at 3 factorial. Do you guys kind of see that 3 factorial would be 3 times 2 times 1? So then on the bottom, we could have just had 3 factorial. And then it would have been fine just to cancel them like this too. Right? So you might see it written that way as well. All right, so let's do one with a variable in it. Okay, so in this one, we're going to follow the same pattern, right? So we'll start with n plus 2. And then just always ask yourself, what's 1 less than n plus 2 or whatever you're dealing with? Well, that would be n plus 1, right? That'd be 1 less. And then the next one would be n. And then you'd keep going, right? So what I'm going to do here is my keeping going would really just be calling this n factorial. But really, the next one would be n minus 1, n minus 2, dot, 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 3 times 2 times 1, right? It would keep going forever. But I can just call this n factorial because that means the same thing. Okay, so I'm going to leave it at n factorial over n factorial, and then I can cancel those. So in the end, this is all the same thing as just n plus 2 times n plus 1. And then you could expand that out too, and that could be written as n squared plus 3n plus 2. All right, next one. So we've got n minus 1 over n, there's factorial over n plus 2 factorial. So, I'm actually going to expand the bottom to kind of show you how this is going to look here, because on the bottom here, this would be n plus 2, and then n plus 1, and then n well, just n, yeah. And then the next one would be n minus 1. And again, I'm just going to call that factorial, right? Because that just keeps on going forever. And the top is already n minus 1 factorial. So now I'm good to go, right? Do you see why I did the bottom first, though? Because I really wanted to make it the same as the top, right? If I did the top and expanded that all out, well, that wasn't going to get me any closer to n plus 2. It was actually going to get me farther away, right? So, okay, so now we can cancel. We get rid of the factorials, and we end up with, well, there's still 1 on top, and then on the bottom, we've got n plus 2 times n plus 1 times n. And yeah, that's fine. I don't need to expand that. I'll just leave it like that. All right, next one. So the next one here, we can say the top here would just be, all right, I'm going to rewrite this as n times, and then the next one would be n minus 1. Okay, that's looking good already. I'm just going to call that n minus 1 factorial because it goes on like that forever. Over, and then the bottom's already the same. N times n minus 1 factorial. So everything cancels, it looks like, and we end up with just 1. Okay, so we can also solve factorials as well. So in this case, well, when we're solving these, what we got to do really is get rid of the factorials. I don't really know how to like deal with factorials, like when we're solving. So we want to get rid of them, doing the same method we did above, right? So very first thing I'm going to do is I'm going to rewrite the top of this. So this would be n times n minus 1 times, and then this looks good, n minus 2, I'll call that factorial, over n minus 2 factorial is equal to 42. And then these nicely cancel, right? N minus 2, n minus 2. So we end up with n times n minus 1 is equal to 42. And then you guys should be well aware how to solve for these now, right? So we expand those. So we get n squared minus n is equal to 42. So we get n squared minus n minus 42 is equal to 0. And then factoring this, we get n minus 7, n plus 6 is equal to 0. So n is equal to 7 from this one, and n is equal to negative 6 from this one. But now, one of these is extraneous. You're probably guessing the right one. Negative 6 doesn't make any sense for my n value, right? So when we're doing these, they're actually going to be our natural numbers, right? So greater than 1. Because I can't really start off with like negative 6 factorial, right? Like negative 6 factorial like that. Because if I start counting down from that, the next one would be negative 7. And then the next one would be negative 8. And then negative 9. Do you see how I'm getting farther and farther away from 1? So that doesn't actually work. I have to be dealing with numbers that are like, well, natural numbers. Okay? So those negative numbers just won't work. All right. So now, if you combine the things we did at the beginning there with the spaces, right? When we were making like our spaces and counting down, like there were a couple of cases where we had like 7, 6, 5, right? Situation like that. If we combine those with our factorial notation, we're into something called permutations, which it really just is, again, just the number of ways. It's just kind of like another way of writing it. So let's say if we just go down a little bit, right? In this example, it says if there are 7 members on the student council, then how many ways can the council select 3 students to be the chair, the secretary, and the treasurer of the council? So using the fundamental counting principle, right? If we were just to make our blanks, well, we could say if there's 7 members, then, well, the first spot, there could be 7, and then 6, and then 5, right? So that's really what this is. There's 7 times 6 times 5 possible ways to fill those positions. We're just going to do the same thing using permutation, like a permutation form here. So yeah, if we rewrite this, right, as do you see the pattern here that this would have been like 6 times 5 or 7 times 6 times 5 times 4 times 3 times 2 times 1, right? Like written out like this. But then we had to get rid of the 4 times 3 times 2 times 1. Well, the way we can get rid of that is by dividing by 4 factorial, right? Do you see that those would all cancel with all of those? That's really what a permutation is, right? That same thing is, or it can be written in a different way. It can be written in permutation form, right? And the formula for permutations is this. It's going to be NPR, okay? Where R represents the items taken from the set, right? So that's going to be, in this case, would be 3. And N is where you start. A good way to remember this, like in our situation, right? We've got, let's say, 7 different members, is I would think about it this way and say, okay, it's of the 7 members, we're going to pick 3, right? So 7p3. Yeah, but the way this works now is if you put this in your formula, NPR, right, which is n factorial, right? So that'd be like 7 factorial over 7 minus 3 factorial, like in our example. Well, that would be the same thing as 7 divided by 4 factorial, which was just canceling out those, right? That's all it was doing. It was just canceling out what we needed to there, which would be 210. Okay, so example. We can put this into your calculator. Okay, so yeah, if you grab your calculator, you can go into math, and then over to probability there, and then you'll see we've got NPR and NCR, right? Well, we're going to be using NCR soon. So NPR, enter. Now this one with a TI-84 plus, it actually just lets you put it in exactly like it's written there. So it'd be 8, and then P, and then 5, right? And then enter. Okay. So that would be 6,720, right? So we'd say, yeah, 8p5, 6,000, what do they say? 720. Right? And just remember what this is saying. I wrote that kind of weird. This would be the same thing as saying, okay, if you had 5 spots, this would be like going 8 times 7 times 6 times 5 times 4. That would also be equal to 6,720, right? They're doing the same thing, okay? Okay, so now just kind of playing around with some factorials here. Let's show that 5 factorial minus 3 factorial is actually the same thing as 19 times 3 factorial. All right, so how we're going to do this is I'm going to take the first one here, this 5 factorial, and I'm going to write this as 5 times 4 times 3 factorial. And then it's going to be that minus 3 factorial. So now, from that, what we can do is we can say, okay, well, what if I just factored a 3 factorial to this whole thing? So this would be the same thing as 3 factorial times 5 times 4 minus 1, which would be the same thing as 3 factorial times 19, or 19 times 3 factorial. Okay. Solve for, okay, so now it's written in this form and it wants us to solve. This isn't going to be very useful the way it's currently written. So what I'd rather do is write out our equation, right? So that's going to be n. So yeah, we've got np2 is equal to 56. So I'm going to rewrite this guy as n factorial, just using my equation, right, over n minus 2 factorial is equal to 56. So now from that, we can do a little bit with this, right? So I want to have n minus 2, so I'm going to expand the top. So let's write this out. This would be the same thing as n times n minus 1 times n minus 2 factorial over n minus 2 factorial is equal to 56. So now we can see that the n minus 2's cancel. And we are left with n times n minus 1 is equal to 56. Okay, so that's not too bad now. So we can expand that out. So we're going to get n squared minus n is equal to 56. So n squared minus n minus 56 is equal to 0. So we get n minus 8 and n minus 7 are equal to 0. So our answer, oh, sorry, plus 7, I mean, my bad. So in the end here, this is going to be, okay, well, n is equal to 8 and negative 7. But we know that's not true, right? It can't be negative 7. So our only real answer here is going to be n is equal to 8. All right, moving on. Okay, so it says use permutations to determine how many arrangements there are of 2 letters from the word Sylvan. Okay, so this is the same thing we were doing before, right? With like the spaces. So we could say, okay, before it would have been 2 spaces, right? There was 6 to choose from. So it would have been 6 times 5. So I'm expecting my answer is 30. This would be the exact same thing as saying of the 6 letters, we're going to pick 5 of them. So that's also 30. Okay, I'm just going to jump down to the last one here too. So 5 letters from the word formula. All right, so this is just going to be the same thing as 7P5. 7 pick 5. So that's 2,520. Okay, so this one says vehicle license plates consist of 3 different letters followed by 4 different digits. If the letters I, O, Y, and Z are not used, determine the number of different license plates they can make. Okay, so if I was going to write that out using the fundamental counting principle, that would be 1, 2, 3, 2, 3, 4, right? So 3 different letters to begin with, right? So if we take away these letters, right, because we're not allowed to use them, then we've got, well, so 26 minus our 4 here, so there's only 22 left, right? 26 in the alphabet minus 4, we've got our 22, and then they can't repeat, right? Oh, you know what? It didn't say it can't repeat, did it? We're going to assume that they can't repeat. Okay, so it'd be 22, 21, and 20, right, for those first spots. So those are our letters, right? That's a letter, that's a letter, that's a letter. And then our numbers are going to be the next ones, right? So then it's going to be, well, no restrictions on the numbers. So there'd be 10 for the first one, and then 9, and then 8, and then 7, right? So those are our numbers. Okay, and that says, oh, sorry, let's write the numbers. The number for that, or the answer there, was large. Okay, so now it says use permutations to find the answer. Okay, so we can use permutations from above by just kind of focusing on the first part and the second part. So for the letters there, that'd be the same thing as saying of the 22 letters to choose from, we're going to pick 3 of them, right? That is what this is saying right there. And then we just multiply that by, of the 10 numbers that we can pick from, we're going to pick 4 of them. And if you did that, we would end up with the exact same answer. All right, last question. All right, so solve this algebraically. Okay, so if we've got, well, here, you know what? Let's actually just kind of simplify this first part to begin with. So if we've got n minus 1, p2, okay, then here my equation was npr is equal to n factorial over n minus r factorial, right? So we're going to stick to the same rules here, right? But on the top now, it's going to be n minus 1 factorial, right? Because that's what this spot is, right? So we'll say n minus 1 factorial over, and then it was n minus r. So in this case, though, it's going to be, I'm going to use 2 brackets. It'll be n minus 1 minus 2 factorial. Okay, So hopefully that made sense. And then this was all equal to 90. We'll just keep in mind, right? All right, so simplifying this down, this was n minus 1 factorial. And then I'm going to rewrite the bottom, right? I'm just going to combine those. Because n minus 1 and then minus 2, if I just ignore the factorial, I'll just do inside the brackets there. That would be the same thing as n minus 2. Oh, sorry, n minus 3 factorial. Okay, and then from here, that's equal to 90. I'm just going to expand the top out. So we'll write this now as n minus 1. And then again, what's 1 less than n minus 1? People, this trips people up. 1 less than n minus 1 is n minus 2, right? So don't go the other way. So it's n minus 2 and then n minus 3 factorial. So we can cancel that on the bottom. And then you can see what happens here, right? So that's equal to 90. And those cancel. All right, and I think you guys are probably good from here, but I'll keep going anyway. So we've got n minus 1 times n minus 2 is equal to 90. And we'll expand that out, so we get n squared minus 3n minus plus 2, is equal to 90. So then n squared minus 3n minus 88 is equal to 0. And then we'll factor. So we get n minus 11 and n plus 8. So our answer here would be, well, really just this one in the end, right? It's going to be n is equal to 11. This one would be n is equal to negative 8, but we know that that's not really going to be an answer for us. So then, yeah, so there's our answer. Okay, this lesson's getting pretty long, so I'll let you guys kind of go through the hints and just kind of use that to your advantage there, but I'm going to end that one there.